2 minutes and 18 seconds. That is the longest anyone on this planet will see the sun go completely dark tomorrow, and the place it happens is open water, 44 kilometres west of the last cliffs in Iceland, where nobody will be standing. Spain gets about a minute at sunset with the sun almost touching the horizon, and the eclipse is only one of 4 things arriving tomorrow. 6 planets before dawn, the Perseids peaking after dark under a moon that is not there, and a geomagnetic storm forecast underneath all of it. 4 events, 1 rotation of the Earth. Except almost nothing being shared about tomorrow is actually correct, including which of those 4 exists at all. If you want the version with the real numbers in it, subscribe to the Skylab and hit that like button on the way past. Then drop a comment telling me where you are watching from and how much of the sun your part of the world actually gets tomorrow. Let's get into it. Part 1. The Shadow. Nobody will be standing under. Tomorrow afternoon, the moon is going to switch off the sun, not dim it, not take a bite out of it. Switch it off completely, for a little over 2 minutes, along a narrow strip of the Earth's surface that runs from the Arctic down through the North Atlantic and finishes in the Mediterranean at sunset. I want to start there, and I want to be very precise about it, because the single most repeated claim about tomorrow is wrong. Across social media right now, on posts with millions of views, August 12th is being described as a partial solar eclipse. It is not. It is a total solar eclipse. That is not a small correction. That is the difference between the most common kind of astronomical event and one of the rarest experiences available to a human being standing on this planet. A partial solar eclipse happens somewhere on Earth several times a year. The moon slides across part of the sun's disk, the light dims by an amount most people never notice, and life continues. A total solar eclipse is a different thing entirely. The moon covers the sun completely. The sky goes dark in the middle of the day, stars come out, the temperature drops, and around the black disk where the sun used to be, something appears that you cannot see at any other time from the surface of this planet. The corona, the sun's outer atmosphere, streaming out in pale white filaments across a sky that has no business being dark. So the first thing to understand about tomorrow is that the version of it that has gone viral has quietly removed the rarest thing on the schedule. Here is the second thing, and it is stranger. The best seat for this eclipse is on the ocean. The maximum duration of totality tomorrow is 2 minutes and 18 seconds, and that maximum occurs at a specific point on the Earth's surface, and that point is water. It is roughly 44 7/10 of a kilometre west of Latrebjarg, in Iceland, out past the westernmost cliffs of the country, in the open North Atlantic. The single longest, deepest, most complete moment of this entire event happens where essentially nobody will be standing, because there is nothing to stand on. The instant of greatest eclipse, the moment when the axis of the moon's shadow passes closest to the centre of the Earth, falls at 17 hours, 45 minutes and 53 seconds, universal time. Iceland as a whole is inside the shadow from 17 hours, 43 minutes and 28 seconds until 17 hours, 50 minutes and 7 seconds. That is a window of 6 minutes and 48 seconds, during which some part of Iceland is experiencing totality. But no single point in Iceland gets anywhere near 6 minutes. Each individual location gets about 2, because the shadow is moving through, not sitting still. Let me explain what that shadow actually is, because the geometry here does all the work. When the moon passes between the Earth and the sun, it casts 2 shadows at once. The outer one is called the penumbra, and it is enormous. A grey oval thousands of kilometres across, inside which the moon is blocking part of the sun but not all of it. If you're standing in the penumbra, you are seeing a partial eclipse. Everyone from Alaska to North Carolina, across most of Canada, across most of Europe, and into northwestern Africa, will be standing in the penumbra tomorrow. The inner shadow is called the umbra, and it is small. It is the part of the shadow where the moon blocks the sun entirely. Tomorrow that umbra is about 293 kilometres wide at its broadest. 293 kilometres, on a planet that is 12,742 kilometres across. That ratio is the whole story of why total solar eclipses feel so impossible to catch. The shadow that produces totality covers about 2% of the Earth's diameter. It draws a line, not a region. And it does not linger. It is worth describing what actually happens inside that line, because most people have only ever experienced the penumbral version, and assume the total one is a more intense edition of the same thing. It is not. It is a sequence, and it runs fast. For an hour or so beforehand, nothing much seems to be going on. The moon takes a notch out of the sun and slowly widens it, and if you are not looking through a filter, you would not know. Then, in the last few minutes, the light starts behaving oddly. Shadows sharpen because the sun has stopped being a disk and become a thin crescent, which is a much smaller light source, and therefore casts much harder edges. Colours flatten out. The temperature begins to drop measurably. In the final seconds, some observers see shadow bands, faint, rippling lines of light, and dark sliding across flat pale surfaces like the bottom of a swimming pool, caused by the last thread of sunlight being scrambled by turbulence in our own atmosphere. Then the last of the photosphere breaks up. The moon is not a smooth ball. It has mountains and crater rims along its edge, and the final sliver of sunlight shines through the valleys between them and is blocked by the peaks. That produces a string of separate points of light around the lunar limb, called Bailey's beads. The beads wink out one by one until a single one is left, and that last bead sitting against the emerging ring of the corona is the diamond ring. And then it is gone, and it is night, and the corona is there. That entire final act takes seconds, and in Spain tomorrow, the whole of totality between the two diamond rings will last about as long as it takes to read this paragraph twice. Now, NASA's own description of tomorrow is worth quoting exactly because it is a great deal more restrained than what is circulating. On August 12th, a total solar eclipse will sweep across Greenland, Iceland, northern Russia, the Atlantic Ocean, Spain, and a small corner of Portugal. Many other places in the northern hemisphere will experience a partial solar eclipse that day, including parts of the northern United States, most of Canada, much of Europe, and northwestern Africa. That is the whole event, stated plainly. A thin line of totality and a very large region of partiality around it. And here is the sentence from NASA that I think should have gone viral instead of the gravity claims and the comet claims and everything else, because it tells you what tomorrow actually is. For most in the path of totality, the sun will be fully eclipsed for less than 2 minutes. Less than 2 minutes. That is what people are crossing oceans for. Kelly Korek is the Eclipse Program Manager at NASA headquarters in Washington, and she framed the scientific stakes this way. From our unique perspective on Earth during a total solar eclipse, she said, scientists can study the sun's corona in a way we can't from anywhere else in the solar system. The sun impacts our daily life, satellites, and astronauts in space, and we can take advantage of this moment to advance our understanding of that influence. I want you to sit with the first half of that sentence, because it is doing something remarkable. We have spacecraft parked in orbit around the sun. We have instruments that have flown through the outer corona itself, and the head of NASA's Eclipse program is saying that for certain kinds of observation, the best vantage point in the entire solar system is a person standing on the ground in Iceland, during the 2 minutes when the moon happens to be exactly the right size and exactly the right distance to blot out the disk and leave the atmosphere behind it exposed. That is not sentiment. That is a statement about optics, and we are going to come back to it. Now, the eclipse is only one of 4 things happening tomorrow, and this is where the day gets genuinely unusual. Before dawn, 6 planets will be spread across the eastern morning sky. In the afternoon and evening, the moon's shadow crosses the Earth. After dark, the Perseid meteor shower reaches its peak, under a sky with no moonlight in it at all. And running underneath all of that, the NOAA Space Weather Prediction Center issued a forecast less than a day ago calling for geomagnetic storming on August 12th, which raises the possibility, small but real, that somebody somewhere on that eclipse track sees the aurora during totality. 4 events. 1 rotation of the Earth. That is the version being shared, and it is broadly true, and it is also, as we're going to see, not quite the right way to count them, because 2 of those 4 things are not 2 things. They are 1 geometric fact with 2 consequences 12 hours apart, and once you see that, the whole day reorganizes itself into something more interesting than a coincidence. But before any of that, there is a more immediate problem, and it is a mechanical one. That shadow has to travel from the Arctic to the Mediterranean. It has a fixed amount of time to do it, and the speed it has to move at is the reason almost everybody on the path gets less than 2 minutes. Part 2, 8,000 kilometers. In 96 minutes. Here is the number that explains almost everything about tomorrow's experience. The Moon's inner shadow will travel 8,260 kilometres across the surface of the Earth. That is 5,130 miles, and it will do it in 1 hour and 36 minutes. Work that out and you get an average ground speed of roughly 5,160 kilometres per hour. Nothing that humans have ever built for routine use travels that fast in the atmosphere. A commercial airliner cruises at around 900 kilometres per hour. Concorde, at its peak, managed a little over 2,000. The shadow tomorrow is moving at more than twice the speed of the fastest passenger aircraft ever flown, and it is doing it across the ground in a straightish line without stopping. That is why totality is measured in seconds. You're not waiting for an event, you're standing still while an event runs over you. The march goes like this. The shadow first touches the Earth up near the Arctic, and the first landfall of any consequence is a remote region of northern Siberian Russia, where, because of where the sun sits in the sky at that latitude and that hour, totality happens around the middle of the day. From there the umbra sweeps southwest, crossing eastern Greenland. Then the west coast of Iceland, in the late afternoon and early evening local time. Then out into the open North Atlantic, where it spends the great majority of its journey. Then it clips the very northwestern tip of Portugal, crosses northern Spain in the late evening, and finally lifts off the Earth entirely out over the Mediterranean, near the Balearic Islands, right at sunset. Most of that path, the great majority of those 5,130 miles, is over empty ocean. The rarest event of the decade spends most of its existence somewhere with no witnesses. There is a second effect that matters enormously for the people at the end of the track, and it has to do with the angle. Near the middle of an eclipse path, the shadow hits the Earth close to straight on. It is roughly circular, it moves at its minimum speed, and totality lasts the longest. Toward the ends of the track, the shadow is arriving at a glancing angle, striking a curved surface almost sideways. The shadow's footprint stretches out into a long ellipse. It races across the ground faster, and the sun sits very low in the sky. Spain is at the end of the track, which means Spain gets a low sun, a stretched shadow, and a short totality. We will come back to exactly how short. There is a way to feel this that does not require any mathematics. Take a torch and shine it straight down onto a table. You get a tight, bright circle. Now tilt the torch until the beam is skimming across the surface at a shallow angle. The same beam becomes a long, smeared oval, dimmer, spread out across far more of the table. That is what the Moon's shadow is doing to the Earth at the start and the end of tomorrow's track. Nothing about the shadow itself changes, only the angle it lands at, and that angle also determines where the sun sits in your sky, which is why the Russian end of the path gets totality at midday, and the Spanish end gets it minutes before sunset. It is the same event. It is a completely different experience. There is one more consequence of the shadow's speed that is worth understanding, because it explains something about the campaigns we're going to look at later. That 5,000 kilometers an hour is an average across the whole track. The shadow is at its slowest near the middle of the path, where it is hitting the Earth most directly and fastest at the two ends, which means the place where totality lasts longest and the place where the shadow moves slowest are the same place. And tomorrow, that place is the North Atlantic, west of Iceland, over water. If you wanted to design an eclipse to be maximally inconvenient for human beings, you would have a hard time improving on this one. There is one settlement worth naming on the northern half of the path, and it is Nuuk, the capital of Greenland. Nuuk gets 79% coverage. 79% sounds like a lot. It is not totality. It is not close to totality in the way that matters. Nuuk sits outside the line. For the enormous population that is not on the path at all, the partial phases roll around the globe in a specific order, and it is worth knowing when to look. The partial eclipse begins as the day begins in northern Russia. In Alaska and northern Canada, the eclipse starts and ends in the morning. Canada's eastern provinces get it in the afternoon. In the northern contiguous United States, the partial phase begins around midday and lingers into the mid-afternoon for those farther east. And the eclipse reaches the United Kingdom, Ireland, mainland Europe, and Africa in the evening. That evening timing produces one of the most beautiful and least discussed variants of the whole phenomenon. For many observers along the western part of the eclipse path, in mainland Europe and in Africa, the sun will set while it is still partially eclipsed. The sun goes down behind the horizon with a bite taken out of it. A sunset eclipse. If you are anywhere in Western Europe or Northwest Africa tomorrow evening with a clear western horizon, that is what you're getting, and it is worth being outside for. Now, a historical note, because the anniversary is almost too neat. The last time a total solar eclipse crossed mainland Europe was August 11th, 1999. Tomorrow is August 12th, 2026. That is 27 years, and the date falls one single day short of the exact anniversary. If you're old enough to remember the 1999 eclipse, the one that crossed Cornwall and northern France and Central Europe, that filled the front pages, that a generation of people in Britain remember mostly as a very expensive lesson in the reliability of August cloud, then tomorrow is the first repeat you have been offered in your adult life. And here is the thing that I suspect most people watching have not registered. The crowds are not going to Iceland. Iceland is expensive, remote, and its weather is famously uncooperative. The crowds are going to Spain because Spain has roads and hotels and 100,000 square kilometres of accessible ground under the path. Spain is also, of the three land masses on the track, the one that gets the shortest, lowest and most fragile version of the entire event. Damn. Part 3. 1 minute at sunset. Every headline about tomorrow carries the same number, 2 minutes and 18 seconds. Spain will get about a minute. That is not a rounding error or a pessimistic estimate. It is the geometry of being at the far end of a shadow track. Along the Spanish centerline, the line running roughly through Oviedo and Leon, where totality is longest in the country, the duration is around 1 minute and 48 seconds. Move off that centerline, as almost every observer will, and it drops further. A great many of the people who travel to Spain for this will experience totality for somewhere between 45 seconds and a minute and a half. Look at what that means in practice. It takes most people a few seconds to register that it has actually happened. It takes a few more to get the eclipse glasses off and look up. Photographers lose another chunk of it to their equipment. The entire event, for a large fraction of the crowd, will be over before their eyes have finished adjusting. Here is the timetable, as NASA publishes it, in local time. In Leon, in northwestern Spain, the partial phase begins at 7:32 in the evening. Totality begins at 8:28. Totality ends at 8:30. The partial phase ends at 9:22. In Zaragoza, further east, the partial phase begins at 7:34. Totality runs from 8:29 to 8:30, and the eclipse is still in progress when the sun sets at 7 minutes past 9. In Valencia, on the Mediterranean coast, the partial phase begins at 7:38. Totality runs from 8:32 to 8:33, and again the sun sets at 1 minute past 9 before the eclipse is finished. Read those timetables again and notice what they're telling you. This is an evening event. In 2 of those 3 cities, the sun goes down before the moon has finished crossing it. That has consequences. When totality occurs with the sun only a few degrees above the horizon, you are not looking up, you are looking out. Which means you need an unobstructed view to the west. No hills, no buildings, no trees. It also means the light from the corona is travelling through the thickest possible slab of atmosphere on its way to your eye, which softens it and reddens it. Some eclipse chasers will tell you that a low-altitude totality is the most beautiful version there is, because the darkened sun sits in a band of sunset colour, and the shadow of the moon can be seen racing across the landscape rather than dropping from overhead. Others will tell you it is the most fragile version there is, and they are also right, and here is why. The shadow makes landfall on the Atlantic coast of Spain, Galicia, and then Asturias, and the Cantabrian coast. In August, that coastline is prone to low cloud and coastal stratus, particularly in the evening as the land cools and the marine layer pushes inland. And when the sun is only a few degrees up, a cloud bank does not have to be thick or extensive to erase the event completely. It just has to be sitting on the western horizon. That is the single largest unknown in this entire story, and it will be resolved within about 24 hours. Every piece of orbital mechanics in tomorrow's schedule has been known to the second for centuries. Whether a low cloud deck sits over the Bay of Biscay at 8:30 tomorrow evening is a question that no one could have answered a week ago, and that thousands of people will be refreshing their forecasts about tonight. And the cruelty of a low-altitude eclipse is that cloud does not have to cover the sky to ruin it. If you're looking at something directly overhead, A broken cloud field gives you gaps, and you take your chances with the timing. If you're looking at something 4 or 5 degrees above the horizon, you're looking through a very long, very shallow slice of atmosphere, and a single bank of stratus sitting 50 kilometres out to sea, cloud that from where you're standing looks like nothing more than a grey smudge along the edge of the world, is directly in your line of sight, and there is no gap to wait for. This is also why so many people making the trip are keeping their plans deliberately loose. Experienced eclipse chasers do not book a spot. They book a region, watch the models for the final 48 hours, and drive, sometimes hundreds of kilometres on the morning itself, to whichever part of the track has the best chance of a clear western horizon. Some will end up inland on the Meseta, away from the coastal cloud entirely. Some will end up on the Mediterranean side, where the shadow arrives last and the sun is lowest of all. Contrast all of this with Reykjavik. In the Icelandic capital, the partial phase begins at 4:47 in the afternoon. Totality runs from 5:48 to 5:49. The partial phase ends at 6:47. Same eclipse, 3 hours earlier in the day, with the sun considerably higher in the sky and none of the sunset fragility. Now, we covered the historical framing of this eclipse on August 2nd, the 27-year wait for mainland Europe, the far longer wait for Spain, and what a scheduled loss of solar generation means for a continental power grid. I'm not going to walk through that again. What I want to add tonight is a number from the far end of that story because it changes the picture. The last time a total solar eclipse crossed mainland Spain along essentially this same track was the 30th of August, 1905, 121 years ago. And there is one more thing in the Spanish timetable that almost nobody has picked up on, and it is the point where the whole viral version of tomorrow starts to come apart. Madrid is listed at 99% coverage. Barcelona is listed at 99% coverage. Both of them are outside the path of totality. Part 4. The 99% trap. 99% is not almost totality. 99% is a different event. This is the single most important thing I can tell you about tomorrow, and it is the thing that separates people who understand eclipses from people who have only read about them. The corona does not fade in gradually as the moon covers more of the sun. It does not get slightly more visible at 90%, and then a bit more at 95, and then quite a lot more at 99. It is not there at all, and then it is there. It appears the instant the last sliver of the sun's surface disappears behind the moon's edge, and it vanishes the instant that sliver comes back. There is no gradient. There is a threshold. The reason is brightness, and the numbers here are genuinely difficult to intuit. The surface of the sun, the photosphere, the part you see as the disk, is roughly 400,000 times brighter than the full moon. The corona is beautiful and enormous, but it is faint, comparable in brightness to a full moon. So as long as any part of the photosphere is visible, even a sliver representing 1% of the disk, that sliver is putting out so much light that it drowns the corona completely and floods your eye and floods the sky. And human brightness perception makes it worse, because it is logarithmic rather than linear. Your eye is built to handle an enormous range of light levels by compressing them, which means that when the sun is 90% covered, the world does not look 90% darker. It looks like a strange, slightly flat, slightly cold overcast. Most people would not notice it if they were not told. At 99% the light gets genuinely eerie, colours go strange, shadows sharpen, the temperature drops. But it is still daylight. It is still, unmistakably, day. And then you cross into the umbra, and it is night. That is why hundreds of thousands of people will drive across a country tomorrow to move themselves a few dozen kilometres, not for 1% more of anything, for the only percent that matters, and the effects that cross that threshold are not subtle once you are on the right side of it. Inside the umbra, the air temperature can fall by several degrees in a couple of minutes, because you have just removed the entire heat source. The wind often shifts, sometimes noticeably, as the sudden cold patch under the shadow disturbs the local pressure field. Birds go quiet or go to roost. Cicadas and crickets, in the right climates, start up as though evening had arrived. Livestock in fields have been observed heading for barns. None of that happens at 99%, because at 99% it is still, from the point of view of every animal and every thermometer involved, daytime. Then there is the horizon, which is the detail that surprises first-timers most. Because the umbra is only a couple of 100 kilometres wide and you're standing near the middle of it, The edge of the shadow is only 100 kilometres or so away in every direction, and out there it is still daylight. So the sky directly above you is dark enough for stars and planets, and the entire horizon, all the way around, is glowing with a band of orange and pink twilight. 360 degrees of sunset in every direction at once. There is no other circumstance in which a human being sees that. Now let me apply that same logic to the numbers most people watching this are actually going to experience, because I think a lot of you are going to step outside tomorrow expecting something and find nothing at all. Here is NASA's published table of maximum coverage across North America. Fairbanks, Alaska, 37%. Halifax, Nova Scotia, 31%. Bangor, Maine, 24%. Portland, Maine, 19%. Montreal, 18%. Boston, 16%. New York City, 9%. Toronto, 8%. Philadelphia, 7%. Edmonton, 6%. Winnipeg, 5%. Washington, D.C., 4%. Detroit, 3%. And the Associated Press reports Norfolk, Virginia at 2%. Let me be completely direct about what those numbers mean. At 4% in Washington and 3% in Detroit and 2% in Norfolk, nothing will happen that you can perceive. The light will not change, the temperature will not change, birds will not do anything unusual. The only way you will know an eclipse occurred is by looking at the sun through a proper filter and seeing a small notch missing from the edge of the disk. That is worth doing. It is genuinely worth doing. But it is not what the posts are promising, and I would rather tell you now than have you standing in a parking lot tomorrow afternoon wondering what you missed. Europe does considerably better. Dublin gets 94%, Paris and Milan get 92%, London gets 91%, Casablanca gets 87%, Berlin and Vienna get 85%, Oslo gets 83%, Stockholm gets 81%, St. Petersburg gets 79%, Krakow gets 64%, Tunis gets 50%, Dakar gets 37%, Algiers gets 96%, Lisbon gets 95%. At those numbers you will notice something. At 90% and above, in the evening, with the sun already low, the light will go distinctly, memorably wrong, just not dark. And because we are now talking about a very large number of people looking directly at the sun tomorrow, I need to be blunt about safety, and I am not going to bury it at the end as a disclaimer. During any partial phase of a solar eclipse, which is every phase for everyone outside that narrow band, and the phases before and after totality for everyone inside it, it is never safe to look at the sun without proper eye protection. Eclipse glasses that meet the international standard, or a handheld solar viewer, or a purpose-built solar filter. Ordinary sunglasses do not work. It does not matter how dark they are. It does not matter if you stack two pairs. They are not thousands of times darker than daylight, and that is what is required. And there is one specific mistake that causes real, permanent injuries every eclipse, so I want to name it explicitly. Do not look through a camera lens, a telescope, or a pair of binoculars while wearing eclipse glasses or holding a handheld viewer. The optics concentrate the sunlight before it reaches the filter, and the concentrated light will burn straight through it. If you want to use optics, the filter must go on the front of the instrument, not between the instrument and your eye. If you have no filter at all, use a pinhole. Punch a small hole in a piece of card, stand with your back to the sun, and let the light fall on a second surface. You will see a small projected image of the eclipsed sun, and it is completely safe because you are never looking at the sun. This is also, incidentally, why the ground under a leafy tree fills with hundreds of crescents during an eclipse. Every gap between the leaves is a pinhole, and each one projects its own image of what is happening overhead. If you're anywhere with meaningful coverage tomorrow, go and stand under a tree and look down. It is the strangest and easiest thing you will see all day. So that is the first place the viral version of tomorrow breaks apart. Not through a lie, exactly, but through a flattening. The event that people are being told to expect and the event that is actually arriving are separated by a threshold that no amount of enthusiasm can cross, which raises the obvious question. If that threshold really is that absolute, if there is no partial credit, no almost, no nearly, then how long does a given place on Earth have to wait for the real thing? The answer, in one case, is longer than any civilization on this planet has existed in its current form. Part 5. The 170-year gap. Iceland last saw a total solar eclipse on the 30th of June 1954. tomorrow will be the first total solar eclipse visible from Iceland this century, and the next one after tomorrow is in the year 2196. I want to let those three sentences sit next to each other for a moment, because the arithmetic they contain is genuinely difficult to absorb. 72 years since the last one, 170 years until the next. Every single person standing in Iceland tomorrow evening, every child, every newborn, every scientist, every tourist who flew in this week is watching the only total solar eclipse they will ever see from Icelandic soil. Not the only one they are likely to see. The only one that exists in the window of a human life. 170 years ago from tomorrow takes you back to the 1850s. 170 years forward takes you past the lifespan of anyone who will be born this century. That is what is happening in Iceland tomorrow, and almost nobody is talking about Iceland. The mainland European gap is 27 years, as I mentioned. The Spanish gap is the one that has generated most of the coverage, and it comes with a genuine historical argument attached, which I find more interesting than the number itself. The last total solar eclipse over mainland Spain was on the 30th of August, 1905. That is 121 years. But there is a complication, and it is a good one. On the 17th of April, 1912, a rare kind of eclipse called a hybrid crossed northwestern Spain. A hybrid eclipse is one that changes character along its own track, annular at some points, total at others, because the moon's apparent size sits so precisely on the borderline that the curvature of the Earth is enough to tip it one way or the other, depending on where you stand. In 1912, that borderline gave northwestern Spain roughly 1 second of totality. 1 second. The Associated Press notes, as a piece of historical trivia that lands harder than it should, that this eclipse fell within days of the sinking of the Titanic. So now you have an argument. Do you count it? If you count it, Spain has waited 114 years. If you discount it, and most eclipse historians do, on the grounds that a single second of totality along one stretch of coast is not a national event in any meaningful sense, then the answer is 121 years, and 1905 stands. I like that argument because it demonstrates something about astronomy that gets lost in the way these things get reported. Even a fact as apparently binary as when did this country last see a total solar eclipse turns out to have a judgment call buried inside it. The orbital mechanics are exact. The bookkeeping is human. Now, why are these gaps so long in the first place? Why isn't there a total solar eclipse over Europe every couple of years? There are two mechanisms, and they compound. The first is the tilt. The moon does not orbit the Earth in the same plane that the Earth orbits the sun. Its orbit is tilted by about 5 degrees. That sounds small, and in most contexts it would be. But the sun is only about half a degree wide as seen from Earth. So a 5-degree tilt is 10 times the width of the target, which means that at most new moons, and there is a new moon every 29.5 days, the moon passes either above or below the sun from our point of view, and casts its shadow harmlessly into space. Only when the new moon happens to fall near one of the 2 points where the moon's tilted orbit crosses the Earth's orbital plane, points called the nodes, does the shadow touch the Earth at all. That is the first filter, and it cuts the count from 13 new moons a year down to a handful of eclipse opportunities. The second mechanism is distance. The moon's orbit is not a circle, it is an ellipse. Over the course of a month, the moon's distance from Earth varies by roughly 10%, which means its apparent size in the sky varies by roughly the same amount. And the moon and the sun are so close to identical in apparent size that this variation is decisive. When the moon is near the far end of its orbit, it is slightly too small to cover the sun, and even a perfectly aligned eclipse leaves a bright ring of photosphere around the edge. That is an annular eclipse, and there is no totality, no corona, no darkness. It is a 90-something% event with a ring. The 1912 hybrid over Spain was that borderline case, toggling back and forth across its own track. Which brings us to the coincidence underneath all of this, the one that makes total solar eclipses possible at all, and which is genuinely remarkable when you look at it directly. The sun is about 400 times wider than the moon, and it is right now about 400 times farther away. Those two ratios happen to cancel, which means the two objects appear almost exactly the same size in our sky. That is the only reason the moon can cover the sun precisely enough to reveal the corona, and no more. There is no physical law requiring that. It is not a consequence of anything. It is, as far as anyone can tell, an accident of where we happen to be in the history of the Earth-Moon system, and it is temporary. The Moon is receding from the Earth at about 3.8 centimeters a year, measured to millimeter precision by bouncing lasers off the retroreflector arrays left on the surface by the Apollo missions. That recession means that at some point in the future, somewhere in the range of 600 million to a bit over a billion years from now, the Moon will be too far away to ever cover the Sun completely, and total solar eclipses will stop happening on this planet permanently. We covered that in more detail a few days ago in the video on lunar observation, so I will not go over the whole argument again. The relevant point tonight is simply that the window is finite, and everybody who has ever seen a total solar eclipse and everybody who ever will is living inside it. There is one more piece of the machinery worth knowing, because it is the reason anybody can print a timetable for tomorrow at all, and it is far older than modern astronomy. Eclipses repeat, not randomly and not simply, but they repeat on a cycle of about 18 years, 11 days and 8 hours. That period is called the Saros, and it exists because 3 different lunar rhythms happen to come back into step after roughly that interval. The time between new moons, the time it takes the Moon to return to the same node, and the time it takes the Moon to return to the same distance from Earth. Line all 3 up and you get an eclipse with almost identical geometry. The awkward part is the 8 hours. 8 hours is a third of a day, which means that by the time the next eclipse in the series arrives, the Earth has rotated an extra third of a turn underneath it. So the repeat happens at roughly the same latitude and with roughly the same duration, but about 120 degrees of longitude further west. You have to wait 3 full Saros cycles, about 54 years and a month, before an eclipse in the same family comes back to approximately the same part of the world. Babylonian astronomers worked out the Saros without knowing anything about orbits, purely by keeping records for long enough. That is an extraordinary piece of pattern recognition. They could not have told you why the Moon's shadow behaved that way. They could tell you when it would happen again. Everything since then has been refinement, and the refinement has now reached the point where we can state the second at which the Moon's shadow axis passes closest to the centre of the Earth tomorrow, and hand out city-by-city tables that will be correct to within a few seconds. So the geometry is fixed. The gaps are what they are, which means if you want to see totality, the only variable left is where you put yourself. Most people solve that by travelling. One team decided to solve it by not standing still at all. Part 6. Chasing the Shadow. At 50,000 feet. At 50,000 feet above the North Atlantic tomorrow, a NASA WB-57 will be flying east along the eclipse path at 460 miles per hour, with 4 cameras mounted in its nose cone trying to outrun the Moon. It will not outrun the Moon, but it does not have to. It only has to lose slowly. The instrument is called SAMI, the Sci-Fly Multispectral Airborne Imager, and it was built by the scientifically calibrated in-flight imagery team at NASA's Langley Research Center in Hampton, Virginia. 4 cameras, 9 separate wavelengths of visible and infrared light, at least 20 images per second continuously for the entire duration of totality. Here is what that buys. On the ground, at the very best location on the planet, that patch of open ocean west of Iceland, the absolute maximum anyone can observe the corona is 2 minutes and 18 seconds. That is 138 seconds. From the jet flying along the path in the same direction the shadow is moving, totality is stretched to nearly 3 minutes, about 180 seconds, 42 extra seconds. That is what 460 miles per hour and a 50,000-foot ceiling buys you. It sounds like a small return until you do the multiplication. 4 cameras at 20 or more frames per second for 180 seconds is more than 14,000 individual frames. Amir Caspi, the principal investigator on the study, from the Southwest Research Institute in Boulder, Colorado, says he anticipates thousands of images from each camera during those precious 180 seconds. Those 42 extra seconds represent something like a third. More data than any ground observer will collect, in wavelengths no ground observer can access. And that is the second reason for the altitude, and it is the more important one. The shadow is moving at roughly 5,160 kilometers an hour. The jet is doing 740. That is about 14% of the shadow's speed. Chasing flat out at the limit of the aircraft, you can only extend the event by about a third, which tells you something quite stark about the scale of the thing you are dealing with. A high-performance research aircraft going as fast as it can in the right direction barely dents it. But altitude does two things that speed cannot. The first is obvious and, on a day like tomorrow, potentially decisive. At 50,000 feet, you are above the weather. Every cloud deck that could ruin the observation for somebody standing in Iceland or Spain is underneath you. The single largest risk to this entire event, the risk we talked about over the Galician coast, simply does not apply to an aircraft flying in the stratosphere. The second is subtler and is the actual scientific justification. Certain infrared wavelengths coming from the corona are absorbed by water vapour and other gases in the lower atmosphere before they can reach the ground. If you want to observe the corona in those wavelengths, you have to get above the absorbing layer, and the corona has been observed in some of those wavelengths only a few times before, ever. It is worth pausing on the aircraft itself for a second, because the WB-57 is an unusual survivor. It is a high-altitude research platform with a very long fuselage and enormous wings, built for thin air, and NASA operates a small fleet of them out of Johnson Space Center for exactly this kind of work. Atmospheric sampling, instrument testing, and observing things that are easier to see from above most of the atmosphere. It has a nose cone that can be fitted with a rotating stabilized optical mount, which is what makes it useful here. You cannot photograph the corona at 20 frames a second from a platform that is vibrating. And flying an eclipse chase is not a matter of pointing the aircraft at the sun and hoping. The intercept has to be planned to the minute months out. You calculate where the umbra will be at a given instant. You work backwards to a takeoff time and a route that puts the aircraft inside that shadow, travelling in the same direction, and then you fly the profile precisely. Because if you're 30 seconds late to the intercept, you have lost 30 seconds of a 180-second observation, and there is no second attempt. The eclipse does not come back around. So what are they looking for? 3 things, in ascending order of difficulty. First, prominences. Those enormous arches and columns of solar material that get suspended above the sun's surface by magnetic fields, sometimes for weeks, and then either settle back or tear away. 20 frames a second over 3 minutes is enough to watch one change shape rather than photograph it once. Second, the coronal heating problem, which remains one of the genuinely unsolved questions in solar physics. The visible surface of the sun sits at roughly 5,500 degrees. The corona, immediately above it, reaches close to 1,000,000. Heat does not spontaneously flow from a cooler thing to a hotter thing, so something is depositing energy up there, and after decades of work the mechanism is still argued over. Imaging the structures in the corona at high cadence and across multiple wavelengths is one of the few direct handles anybody has on it. And third, the relationship between coronal material and the solar wind. The stream of charged particles that flows out from the sun across the entire solar system and eventually arrives here, which is the thing that drives the geomagnetic storms we cover on this channel constantly. The corona is where the solar wind is born. Tomorrow is one of the few chances to photograph the transition. This is not the instrument's first flight. Sammy flew on a WB-57 during the total solar eclipse of the 8th of April, 2024, the one that crossed Mexico, the United States and eastern Canada. It worked. It also revealed its own limitations. Some of the brightest features in the corona came out overexposed. So for tomorrow, the team has adjusted the exposure time specifically to capture those bright structures properly, and they have built new software since 2024 to process and analyze the data faster than they could 2 years ago. Caspy's framing of why any of this is worth doing at all is the most honest thing anyone has said about tomorrow. The sun is always changing, he said. Every eclipse is different, so we could see things we didn't see before, and we learn from each eclipse how to better observe the next one. And then, more bluntly, it's true the eclipse is short, but it's still incredibly valuable. The experiment is funded through NASA's Heliophysics Low-Cost Access to Space program, which is worth noticing. The most sophisticated observation of tomorrow's eclipse, 9 wavelengths above the weather at the edge of the stratosphere, is running under a program with the words low cost in the title. 3 days ago, we looked at a very different solar instrument, a ground-based telescope pushing right up against the physical limit of what its optics could resolve. Same discipline, opposite approach. One of them buys resolution, this one buys time and altitude. Which brings us to the other campaign flying tomorrow, and it takes the opposite approach again. Instead of chasing the shadow sideways, they are going straight up, and instead of one aircraft, they are launching 80 balloons. Part 7. 80 balloons. For 2 minutes of dark. 80 balloons, 26 hours of continuous launches, all of it aimed at an event that lasts about 2 minutes. That ratio is the shape of eclipse science, and I do not think most people appreciate how extreme it is. The program is the Nationwide Eclipse Ballooning Project. It is supported by NASA, and it is led by Angela Desjardins at Montana State University. It works by sending student teams from several American universities out to the eclipse path, this time to Iceland and to Spain, to launch scientific balloons before, during, and after totality. In Iceland, 2 teams will launch a total of 80 balloons. The launches begin 18 hours before the eclipse and continue until 8 hours afterwards. That is a 26-hour window of continuous atmospheric sampling wrapped around a 2-minute event. And they are all chasing one specific thing, the boundary layer. The boundary layer is the part of the atmosphere that is in direct contact with the ground. It is the layer where the surface actually influences the air, where friction, heat and moisture from the land or the sea mix upward. Its thickness is not fixed. It rises and falls depending on how warm the surface is and how much moisture is in the air. On a hot afternoon over land, the boundary layer can be a couple of kilometres deep, churning with convection. At night, when the ground cools, it collapses down to a few hundred metres or less. And the reason balloons are the right tool is that the boundary layer is a vertical structure, and almost every other instrument we have measures horizontally. A weather station on the ground tells you what the air is doing at 2 metres. A satellite tells you what the top of the column looks like. Neither of them tells you where the transition sits or how fast it moves. A balloon carrying a small instrument package, temperature, pressure, humidity, position, rises through the whole column at a few meters a second and radios back a continuous profile the entire way up. Launch one every 20 minutes for a day, and you have a film of the atmosphere's vertical structure rather than a photograph. That is why the launch schedule matters as much as the launch count. 18 hours of profiles before the eclipse establishes what the boundary layer normally does at that site, on that day, at every hour. 8 hours afterwards establishes how long it takes to recover. Without both of those, a measurement taken during totality is just a number with nothing to compare it to. So here is the question. If you switch the sun off for 2 minutes in the middle of the afternoon, does the boundary layer behave as though night has fallen? They have already partially answered it. Balloon flights during the solar eclipses of October 2023 and April 2024 showed that the boundary layer did collapse. It decreased in thickness at locations where the skies were clear, and critically, it did not collapse where the skies were cloudy. Which makes physical sense. If there is already a cloud deck cutting the surface heating, removing the sun for 2 minutes changes much less. But Iceland in August introduces a genuine complication, and this is why the campaign is interesting rather than routine. Boundary layer behaviour is fundamentally driven by the day-night cycle. It collapses at night because the ground stops being heated. But in Iceland in August, the days are extremely long and the nights are extremely short. The whole diurnal rhythm that the collapse mechanism depends on is muted. So the nighttime influences that helped drive the effect in Indiana in April 2024 may simply not be strong enough at 65 degrees north in the middle of an Icelandic summer. Matthew Bernards, a chemical engineering professor at the University of Idaho who leads one of the Iceland teams, put the entire campaign into a single sentence. Will this eclipse be able to collapse the boundary layer? 80 balloons, 26 hours, and a question you can ask in 9 words. That is a well-designed experiment. Spain gets a different campaign. 3 balloon teams are launching a total of 6 balloons, and these carry 2 payloads. The first is cameras, 360-degree cameras designed to image the eclipse shadow from above. This has been done before, and the results are extraordinary. During the April 2024 eclipse, a camera carried by a scientific balloon at about 90,000 feet photographed the moon's shadow lying on the surface of the Earth, a dark oval sitting on the planet, with the thin blue band of the atmosphere separating Earth from the blackness of space above it. The Spanish balloons are aiming for the same shot over the Iberian Peninsula tomorrow evening. The second payload is ozone instruments, and the reason is elegant. Ozone in the atmosphere requires sunlight to form. It is created when ultraviolet radiation breaks apart oxygen molecules and the fragments recombine. So if you remove the sunlight, ozone production stops, while ozone destruction continues. Similar balloon experiments showed that ozone measurably decreased during totality in April 2024. The open question for tomorrow is whether the same thing happens under different conditions. This eclipse occurs later in the day with the sun already low and in a different season. If the ozone drop is smaller, that suggests the response scales with how much solar flux you actually remove. If it is comparable, that argues the atmosphere responds faster and more sharply than expected. Either answer is worth having. Desjardins summarized the logic of the whole thing in a way I keep coming back to. A couple of minutes isn't a lot of time, she said, but it's still plenty to affect the atmosphere and to make that cold, dark shadow of the moon on Earth. Now, one piece of honest bookkeeping, because the numbers here do not perfectly agree, and I would rather flag that than pretend otherwise. NASA's own description of the campaign gives 80 balloons in Iceland and 6 in Spain. The Associated Press reports the teams launching more than 60 high-altitude balloons in total, and adds that they launched roughly 10 times as many during the 2024 eclipse over North America. Those two accountings do not match exactly. The honest range is somewhere between 60 and 86 balloons, and the more useful comparison is the one about 2024. An eclipse that crosses your own country, with road access along the whole path, lets you fly 10 times the hardware. An eclipse that happens mostly over the North Atlantic does not, which is, again, the theme. Being in position is the hard part, and nothing illustrates that better than the spacecraft that was built specifically to manufacture the exact conditions the moon is going to supply for free tomorrow, and which will be looking the wrong way when it happens. Part 8. The spacecraft that builds eclipses and will miss this one. The European Space Agency operates a mission called Proba-3, and its entire purpose is to create artificial total solar eclipses on demand. In the past 2 years, it has created more than 60 of them. The longest lasted 5 hours and 38 minutes, and tomorrow, when the moon does it for real, Proba-3 will be in the wrong part of its orbit to watch. Let me explain how the mission works, because it is one of the more audacious pieces of engineering currently flying. Proba-3 is not one spacecraft. It is 2, flying in precise formation, separated by a gap of well over 100 meters. One of them carries a disk, the other carries a camera. The disk-carrying satellite positions itself so that its disk blocks the sun, exactly as seen by the camera on the other satellite. What you have built, in effect, is a coronagraph, an instrument for blocking a star so you can see its atmosphere. Except that instead of putting the occulting disk a few centimeters in front of the lens, you have put it 150 meters in front, in vacuum, on a separate free-flying spacecraft. The reason to go to that trouble is that a conventional coronagraph, with its disk inside the instrument, produces a halo of scattered light around the edge that swamps the innermost part of the corona, precisely the region where the most interesting physics happens. Move the disk far enough away and the scattering problem largely disappears, which is exactly why a natural eclipse is so scientifically valuable in the first place. The moon is an occulting disk 384,000 kilometers away, and it produces no scattered light at all. Now put the two numbers side by side. Proba-3 can hold an artificial totality for 5 hours and 38 minutes. Nature's maximum tomorrow is 2 minutes and 18 seconds. On paper, the spacecraft wins by a factor of about 147, and yet the ground campaigns are still flying, and the aircraft is still going up, and thousands of people are still crossing the Atlantic, and the reason is that the spacecraft is not doing quite the same thing. An artificial eclipse gives you the inner corona under controlled conditions for hours at a time. It does not give you the outer corona out to many solar radii, which requires the specific geometry of a real eclipse and a very dark sky. It does not give you the atmospheric response or the boundary layer collapse, the ozone drop, the temperature fall. It does not give you observers distributed across thousands of kilometers of the Earth's surface, all watching the same event from different angles and different altitudes at slightly different times. And it does not give you the horizon effects, the shadow racing across the landscape, or any of the phenomena that only exist because a shadow is landing on a planet with an atmosphere and people standing in it. And there is a reason all of this effort keeps circling back to the corona specifically, rather than to the sun's surface, which we can photograph any day of the week from a dozen spacecraft. The corona is where space weather starts. It is the outermost layer of the sun's atmosphere, it is threaded with magnetic field, and it is the launch point for both of the things that reach us. The steady outflow, the solar wind, is corona that has escaped. The violent events, coronal mass ejections, billions of tons of magnetized plasma thrown outward at hundreds or thousands of kilometers a second, are corona that has been torn loose when its magnetic field reorganizes. Every geomagnetic storm we cover on this channel, every aurora, every satellite anomaly, every induced current in a power grid begins as a structure in that faint white halo that is only visible from the ground for 2 minutes tomorrow, which makes the corona the single most consequential part of the sun for life on Earth, and also the part we are worst at observing. We can see the surface constantly, and the inner heliosphere constantly. The layer in between, the one where the energy transfer actually happens, is the one that requires either a very expensive spacecraft or a very rare shadow. So Proba 3 will do what it can. It will be in the wrong part of its orbit for totality as seen from Earth, but it will try to sneak in some before and after shots. And 2 of ESA's space telescopes will be observing the eclipsed sun and its corona regardless. Andrei Zhukov, of the Royal Observatory of Belgium, who works on the Proba 3 science mission, said something about all this that I think is the most quietly revealing quote of the entire story. "We're looking forward to more eclipses," he said. Natural or artificial? Think about what it takes to say that. This is a scientist who can now order a total solar eclipse the way you would order a measurement. Request the formation, hold it for 5 hours, get the data. And he's still looking forward to the natural one. Not because it is longer, because it is dramatically shorter, because it is different, and because you cannot yet build the whole thing. On the public side, ESA is going substantially further than a data run. The agency will host a live webcast from Spain's Astrophysical Observatory of Javalambre and a public celebration in León, which is, not coincidentally, sitting almost exactly on the Spanish centerline. NASA will run its own broadcast starting at 1:15 in the afternoon, Eastern Daylight Time, with views from both Iceland and Spain. The Italian-based Virtual Telescope project will stream it as well, and Carol Mundell, ESA's Director of Science, gave what I think is the honest institutional answer to the question of why an agency with 2 space telescopes and a formation flying coronagraph is also organizing a party in a Spanish city. "For me," she said, "it's not just a scientific moment, it's not just an incredible alignment of heavenly bodies, it's also a very human moment. It's a real human connection between us, with our feet planted on the Earth and the cosmos." That's the Director of Science at a major space agency saying, on the record, that the value of tomorrow is not entirely reducible to data. I do not think you have to be sentimental to find that significant. Every single campaign we have just walked through, the aircraft, the balloons, the formation flying satellites, the webcasts, the public event in León, exists because being in the right place at the right moment is the genuinely hard part of this, not the physics, the logistics, which is, in the end, what the phrase "nobody is ready" actually means. Not that something dangerous is coming, that being ready would require being in several places at once, and we have only dealt with one of tomorrow's 4 events. The other 3 are running on completely different clocks. 2 of them are real, one of them is not what it appears to be at all. Part 9. The same moon, 12 hours later. Strip tomorrow down to its mechanics and something interesting falls out. The 4 converging events are not 4 events. Here is why. A total solar eclipse requires a new moon. Not usually, not typically, by definition. The only way for the moon to cover the sun is for the moon to be directly between the Earth and the sun, and that configuration, moon between us and the sun, is precisely what the phrase new moon describes. There is no such thing as a solar eclipse at any other lunar phase. It is not possible. Now think about what that means for the night sky. If the moon is sitting between us and the sun, then from where you are standing the moon is up during the day and down at night. It rises around dawn and sets around dusk along with the sun, and it is not illuminated on the side facing us anyway. So on the night of a solar eclipse there is no moonlight. None. The sky after dark is as dark as your location will ever get. And the Perseid meteor shower peaks on the night of the 12th into the 13th of August. So the headline you keep seeing, a total solar eclipse and a perfectly dark meteor shower on the same day, what are the odds, has the causality backwards. The odds are 1. Given an eclipse on that date, the dark sky is not a coincidence. It is a requirement. They are the same geometric fact, observed 12 hours apart, that does not make it less remarkable. If anything, I think it makes it more so, because it means the thing to be amazed by is not luck. It is that a single alignment of three bodies produces one spectacle in the afternoon and clears the stage for a completely unrelated one that night. What is genuinely coincidental is the calendar. The Perseids peak in mid-August every year, driven by where Earth is in its orbit. The eclipse falls when it does because of the lunar cycle. Those two calendars are unrelated, and them landing on the same date is the real coincidence in the story. The dark sky is downstream of it. So let us get the meteor shower right, because there is more nuance here than the posts suggest. The Perseids in 2026 peak overnight on the 12th into the 13th of August. The broad peak likely stretches from around 2100 hours GMT on the 12th until around 0900 hours GMT on the 13th, with the highest rates expected between 2 and 4 in the morning GMT on the 13th. There is also a published predicted peak instant of 1453 Universal Time on the 13th, which is daylight for Europe and the Americas. A reminder that meteor shower peaks do not politely arrange themselves for your time zone. The new moon itself falls on the 12th, and here is a number worth holding on to. A new moon will not fall on August the 12th again until 2045. That is 19 years, and 19 is not an arbitrary number. It is the Metonic cycle, the observation, attributed to the Greek astronomer Meton in the 5th century before the Common Era, that 235 lunar months come out almost exactly equal to 19 solar years, which means the phases of the moonland on the same calendar dates on a 19-year rhythm. It is the reason the date of Easter can be calculated, and it is the reason the next time these two particular things line up is 2045. Now, what is a meteor shower physically? Because this is one of those things everybody has seen and very few people have had explained. The parent body of the Perseids is a comet called 109P, Swift-Tuttle. It is a large comet. Its nucleus is estimated at around 26 kilometres across, and it swings through the inner solar system on a roughly 133-year orbit. Every time it passes near the Sun, the ices in its surface sublimate, and as the gas escapes it drags dust and grit with it. Over thousands of years, that debris has spread out along the comet's entire orbital path, forming a vast, thin, slightly clumpy stream of particles circling the Sun. Earth's orbit intersects that stream. Every August we drive through it. The particles themselves are mostly tiny, sand grains, occasionally something the size of a pea. But they are moving fast. The Perseids enter our atmosphere at around 59 kilometers per second, which is one of the higher speeds of any annual shower. And at that velocity, a grain of sand carries a startling amount of kinetic energy. It does not survive. It compresses and heats the air in front of it, ionizes a channel of atmosphere around 80 to 120 kilometers up, and that glowing channel is what you see as a meteor. The particle is destroyed entirely, tens of kilometers above your head, which means that every one of the streaks you see tomorrow night is a piece of a comet that has been travelling on its own orbit for centuries, arriving at the end of its existence in a line of light that lasts less than a second. Swift-Tuttle itself deserves a sentence because it is not a minor object. At an estimated 26 kilometers across, it is larger than the impactor generally associated with the end of the dinosaurs, and its orbit crosses ours. It was last at perihelion in 1992, and when its orbit was recomputed after that pace, there was a brief and genuinely serious discussion in the astronomical community about a possible close encounter in the year 2126. Further observations tightened the orbit and eliminated the concern. The 2126 pass will be a comfortable miss. But for a short period in the early 1990s, the parent body of the most popular meteor shower in the Northern Hemisphere was on a watch list. So when you look up tomorrow night, you're watching the exhaust trail of an object that is, in the long run, a genuinely significant piece of the solar system's inventory. The shower is beautiful. The thing that made it is 26 kilometers of ice and rock on a 133-year orbit that happens to intersect our own. The radiant, the point in the sky the meteors appear to come from, sits in the constellation Perseus, which is what gives the shower its name. That is a perspective effect. The same reason snow appears to come from a single point ahead of you when you drive through it. The particles are travelling in parallel, you are seeing them converge, and there is one place on Earth tomorrow that gets both halves of this in a single night. Northern Spain sits under the path of totality in the evening, and under a completely moonless sky a few hours later. Totality at 8:30, and the Perseids at their peak in the small hours. Nowhere else on the planet gets that combination. The Associated Press even raises a possibility I had not considered. Meteors could photobomb totality itself. During those 2 minutes, the sky is dark enough to show stars and the brighter planets, so a Perseid streaking through the frame while somebody's photographing the corona is not out of the question. Improbable in a 2-minute window, but not impossible. Practically none of this requires equipment. No telescope, no binoculars. Binoculars actually hurt, because they narrow your field of view and meteors can appear anywhere. What you need is a wide-open sky, no direct light sources in your eye line, something to lie back on, and patience. Specifically, about 20 minutes of patience, because that is roughly how long it takes for your eyes to dark adapt properly, and almost nobody waits it out. People go outside, look up for 4 minutes, see nothing, check their phone, which destroys the adaptation instantly, and go back in. So the honest count of tomorrow is not 4 events. It is 1 geometry with 2 visible consequences, plus whatever the other 2 turn out to be, and that recount is where this gets more interesting rather than less. But there is a second problem with the meteor shower, and it is a bigger one. Everybody is quoting one number for the rate. The organisation that actually models the debris stream is quoting a very different one. Part 10. The number nobody is quoting. Here are 2 forecasts for tomorrow night, both of them legitimate, and they do not agree. The number in almost every article and every post is up to 100 meteors per hour. The number in the International Meteor Organization's modelling is no higher than 43. That is not a small discrepancy. That is a factor of more than 2, and the lower figure comes from the people whose actual job is modelling where the debris is. Let me set out what the IMO's shower calendar actually says, because the detail matters. It notes that Perseid activity may be lower in 2026, before increasing again in 2027, as the Earth encounters parts of the stream that have been disturbed by Jupiter. It models 2 specific encounters. Earth may pass through a branch of a dust trail released in the year 1079 on the 12th of August at about 1653 GMT, followed by a weak filament around 0100 hours GMT on the 13th. Both of those come with a timing uncertainty of roughly 5 hours in either direction. And the modelled zenithal hourly rate for those encounters is no higher than 43. There are 3 things in that paragraph worth pulling apart. The first is the phrase zenithal hourly rate, which is the most misunderstood number in all of meteor astronomy, and the reason so many people come away from meteor showers disappointed. Zenithal hourly rate is not a prediction of what you will see. It is a standardized laboratory figure. It describes how many meteors a single observer would count in 1 hour if, and these conditions are almost never met. The sky were perfectly dark with a limiting magnitude of 6.5. The radiant were directly overhead at the zenith, and the observer had an unobstructed view of the entire sky. Every departure from those conditions reduces the real count, and most of them reduce it a lot. If the radiant is halfway up the sky rather than overhead, you lose a large fraction. If you are in a suburb with streetlights, you lose most of the faint ones, and the faint ones are the majority. If there are trees or buildings blocking 1/3 of your sky, you lose 1/3 of your meteors. So even in a good year with a ZHR of 100, a realistic count from a genuinely rural site is 30 to 50 an hour. The 100 is achievable only under exceptionally dark skies with the radiant well placed. From a suburban garden you might see 10, which means that if the IMO's modelling is right and the ZHR tops out around 43, the realistic rural count tomorrow night could be something like 15 to 25 an hour. Under the darkest sky the shower will get for 19 years, and there is a variable in that equation that has nothing to do with comets or with Jupiter, and it has been getting steadily worse for decades. Limiting magnitude, the faintest star you can see from where you're standing, is the single biggest control on how many meteors you count, because the brightness distribution of meteors is heavily weighted toward the faint end. For every brilliant fireball there are dozens of modest streaks and hundreds of barely there ones. Lose a magnitude of sky darkness, and you do not lose a fixed number of meteors, you lose a large fraction of them. A genuinely dark rural sky gets you to magnitude 6 or 6.5. A small town gets you to about 5. A suburb gets you to 4. From inside a large city you may be down to 2 or 3, at which point you can count the visible stars, and the Perseids will produce perhaps a handful of the very brightest events an hour, no matter how good the shower is. So the darkness that the new moon is handing everybody tomorrow night is a gift, and for a great many people it will be entirely cancelled out by the streetlight 40 metres away. If you want any chance at the real numbers, the drive out of town matters more than the date. The second thing worth pulling apart is Jupiter, because the mechanism is genuinely elegant. The Perseid stream is not a uniform tube of dust. It is a bundle of individual trails, each one shed during a different passage of Swift-Tuttle through the inner solar system, each one on a slightly different orbit. And every one of those trails passes through the outer solar system on its way round, where Jupiter's gravity gets a chance to work on it. Over centuries, Jupiter nudges some trails inward and some outward, bunches material in some places and thins it in others. The result is that the density of debris along Earth's crossing point changes from year to year and from decade to decade, in ways that can be modelled if you know the history of the trails. That is what the IMO is doing when it says 2026 may be weaker and 2027 stronger. It is not a guess about the weather, it is a calculation about where 1,000 years of comet dust has been pushed. Which brings us to the third thing, and it is the one I find genuinely striking. The dust Earth may run into tomorrow afternoon was shed by Swift-Tuttle in the year 1079. 1079, that is before the First Crusade. The comet came through, warmed up, threw off a cloud of grit, and that grit has been orbiting the Sun on its own ever since, nearly 1,000 years of quiet, undisturbed travel. And tomorrow, some of it may end its existence as a 2-second streak over a field somewhere, watched by somebody who has no idea what they are looking at. Now, the uncomfortable pairing. Tomorrow night gives the Perseids the best possible conditions. A new moon, full darkness, the peak falling exactly right. And the modelling says the shower itself may underperform. Both of those can be true at once. The sky can be perfect and the shower can be thin. Conditions and activity are independent variables, and the coverage has almost entirely collapsed them into one. I think this matters for how tomorrow gets remembered, and here is why. If a large number of people go outside on a perfect moonless night, expecting 100 meteors an hour because that is the number they were given, and they count 15, the conclusion that will spread is that the whole thing was overhyped. Not that two different numbers were being quoted by two different kinds of source, one of which had a caveat attached and one of which did not. The caveat is where the accuracy lives, and the caveat is the first thing that gets dropped when a fact is passed along. That is the second place tomorrow's viral version breaks, and notice that it broke in exactly the same way the first one did. Nobody lied. A number got separated from its conditions and then repeated until the conditions disappeared. So, 2 of the 4 clocks are now accounted for, and they turned out to be 1 clock. The third is the one people photograph constantly and describe wrongly almost every single time. Part 11. 6 planets, 2 you can actually see. Tomorrow morning, before the sun comes up, 6 planets will be spread across the eastern sky. Jupiter, Mercury, Mars, Uranus, Saturn and Neptune. Now let me tell you what you will actually be able to see. Mars and Saturn are the easy ones. Both are comfortable naked eye objects. Both will be well placed, and if you are outside at the right time, you will find them without difficulty. Mars will be the reddish one. Saturn the steady yellowish one that does not twinkle much. Mercury is harder. Mercury is always harder. It sits low, close to the sun, and it needs a genuinely clear horizon with nothing in the way. No hills, no buildings, no trees, and preferably no haze. Plenty of professional astronomers have gone entire careers without seeing Mercury, which is a fact I find both amusing and slightly comforting. Jupiter, and this is the part that surprises people, because Jupiter is normally the brightest planet in the sky after Venus, will be sitting even lower than Mercury, which means it is the hardest of the 4 bright ones, not the easiest. Uranus requires binoculars. Under a genuinely dark sky, at the very best of times, Uranus can be glimpsed with the naked eye by someone who knows exactly where to look, and even then it is a marginal, arguable thing. In a pre-dawn sky with twilight coming on, you will need optics, and Neptune requires a telescope. There is no negotiating with that one. Neptune has never been visible to the unaided human eye from Earth, in all of history. It was discovered in 1846 by mathematical prediction, and then confirmed with a telescope, and a telescope is what it still takes. So the honest audit of the 6-planet alignment is too easy, too difficult, and 2 that you simply will not see without equipment you probably do not own. The window is narrow too. At mid-northern latitudes, New York, Madrid, Tokyo, all 6 become visible about 30 to 60 minutes before local sunrise. That is the sweet spot, and it is a compromise. The sky needs to still be dark enough to show the faint ones, but late enough that the low ones have actually cleared the horizon. Go out too early and Jupiter and Mercury have not risen. Go out too late and the twilight has washed out everything except Mars, Saturn and possibly Mercury. Now, the word alignment, which is doing an enormous amount of unearned work in every post about this. The planets are not lining up. They are not forming a line in space. They are not arranged in a row extending outward from the Sun. They are scattered across completely different parts of their own orbits, at wildly different distances from Earth, and the only thing they share is that they happen to be on the same side of the sky from our point of view for a few weeks. And even the appearance of a line is not really a coincidence, which is the part that gets left out. Every planet in the solar system orbits in very nearly the same plane, a legacy of the flattened disk of gas and dust the whole system condensed out of 4.5 billion years ago. That plane, projected onto our sky, is a line called the ecliptic, and because every planet is stuck near that plane, every planet always appears somewhere along that same line across the sky. Always. Every night of your life. So a planet parade is not the planets moving into formation. It is a stretch of a permanent arrangement becoming briefly visible at once, because all the members of it happen to be above the horizon in the same part of the night. That same line is the reason the zodiac exists, incidentally. The 12 zodiac constellations are simply the star patterns that the ecliptic passes through, the backdrop against which the sun, the moon, and every planet appear to move. Ancient sky watchers noticed that the wandering objects never strayed from that one band, and built an entire symbolic system on top of the observation. The observation was correct. The system was not. What they had actually found, without any way of knowing it, was evidence that the whole solar system formed flat. And the reason a 6-planet spread makes the news every year or two is that it is a fairly low bar. There are only 7 other planets. Getting 5 or 6 of them on the same side of the sky at once is not a rare configuration. It happens every couple of years, and it will happen again. What varies is how well placed they are, how many are bright, and how aggressively somebody decides to promote it. And the depth of that arrangement is where it gets genuinely humbling. When you look at that line tomorrow morning, the light hitting your eye from Mars left it a few minutes ago. The light from Jupiter left it around 40 minutes ago. The light from Neptune left it more than 4 hours ago. It departed while you were asleep, crossed roughly 4.5 billion kilometres, and arrived at your retina in the same instant as light that left Mars while you were putting your shoes on. You're not looking at a line. You're looking down a corridor billions of kilometres deep, flattened into 2 dimensions by perspective, with the light from each end of it arriving simultaneously, because it's set off at wildly different times. The practical news is good, at least. Unlike the eclipse, this one forgives you. The planets remain visible on several mornings around the 12th, with the layout shifting slightly day to day. If you sleep through tomorrow, the morning after will do nearly as well. The practical news is also this. You need a flat eastern horizon, no obstructions, no significant light pollution in that direction, and you need to be awake and outside about 90 minutes before dawn. That requirement alone is why the overwhelming majority of people who share the graphic will never actually see the thing it depicts, and that is the third of tomorrow's clocks, the first one that is genuinely independent of the moon, not a consequence of the eclipse geometry, not caused by it, just a coincidence of viewing angle that happens to fall on the same date, which leaves the fourth, and the fourth is the only one that nobody can predict, that was updated less than a day ago, and that could, if it goes wrong in exactly the right way, produce something almost nobody alive has seen. Part 12. The Storm That Might Arrive. Late. At midnight, Universal Time, this morning, the NOAA Space Weather Prediction Center published its 3-day forecast. That document is less than 24 hours old, and it is the only part of tomorrow's schedule that is a genuine forecast rather than an ephemeris. Right now, the sky's quiet. The greatest observed 3-hour planetary K-index over the past 24 hours was 2, below NOAA scale levels entirely. Nothing happening. The forecast for tomorrow is different. The greatest expected 3-hour KP for the 11th through the 13th of August is 5.00. That is NOAA scale G1, a minor geomagnetic storm, and the rationale in SWPC's own words is short and specific. G1, minor, geomagnetic storming is likely on the 12th of August due to anticipated CME activity. Anticipated coronal mass ejection activity. Something has left the Sun, or is expected to, and the forecasters think it arrives tomorrow. Here is the hour-by-hour breakdown for the 12th. From midnight to 3 Universal Time, KP2, 3 to 6, 3.67, 6 to 9, 5.00, the G1 window, 9 to 12, 4, 12 to 15, 3.33, 15 to 18, 2.33, 18 to 21, 2.67, 21 to midnight, 3.33. Now put that next to the eclipse. Greatest eclipse is at 17 hours, 45 minutes and 53 seconds Universal Time, which lands squarely in the 15 to 18 bin. And in the 15 to 18 bin, the forecast KP has fallen back to 2.33. So on the forecast exactly as issued, the geomagnetic storm peaks roughly 9 to 12 hours before totality, and by the time the moon's shadow reaches Iceland, the disturbance is expected to have faded. It is worth being clear about what a G1 storm actually is, because the scale runs from 1 to 5 and the word storm does a lot of unearned work at the bottom end. A G1 is minor. Power grid operators may see weak fluctuations. Satellite operators may notice minor effects on spacecraft orientation. Migratory animals that navigate magnetically may be affected at high latitudes. And the aurora becomes visible at high latitudes, typically down to around 60 degrees geomagnetic, which in practice means northern Scandinavia, Iceland, most of Alaska, and the northern edge of Canada. It is not a Kansas aurora. It is not a headline event. It is the sort of disturbance that happens dozens of times a year during an active solar cycle, and that most people never notice. For comparison, the storm 4 days ago that overshot its forecast was a G2, moderate, and that was enough to push the aurora down to a line running from New York through Wisconsin to Washington state. A G5, the top of the scale, is the kind of event that puts aurora over the tropics and takes transformers offline. So the forecast for tomorrow is not a warning. It is a note that the sky at high latitude will be slightly disturbed at a time of day when nobody in the northern hemisphere summer could see an aurora anyway, because at those latitudes in August it does not get dark, except for 2 minutes, in one narrow band, tomorrow afternoon. The rest of the space weather picture is quiet in every respect. The probability of an S1 or greater solar radiation storm is 1% each day, all 3 days. The probability of a radio blackout at R1 or R2 is 1%, and R3 or greater is also 1%. No significant active region flare activity is forecast. Whatever is coming tomorrow is a modest, glancing, unspectacular disturbance, except 4 days ago, on the 8th of August, something happened that is worth putting directly alongside that forecast. A product issued at 12:30 that day said no G1 storming was expected. At 14 minutes past 1, 44 minutes later, the planetary K index reached 5. 22 minutes after that, at 36 minutes past 1, it reached 6. G2. Moderate storm conditions, 2 full-scale levels above what had been forecast less than an hour earlier, following the arrival of a suspected slow-moving coronal mass ejection that had probably left the Sun on the 5th or 6th. Aurora was reported as far south as a line running roughly from New York through Wisconsin to Washington state. 2 scale levels of error, inside an hour, 4 days ago, from the same forecast system. I am not saying that to criticize the forecasters. Space weather forecasting is one of the genuinely hardest prediction problems anybody attempts, because you are trying to estimate the arrival time and the magnetic orientation of a cloud of plasma that you can only see edge on from 93 million miles away, and the single most important variable, which way the magnetic field inside it is pointing, cannot be measured until the cloud is about an hour from Earth. I am saying it because it establishes the size of the error bars. Coronal mass ejection arrival times routinely slip by hours in either direction, and KP is a 3-hour average, not an instantaneous reading, which smooths over exactly the kind of short, sharp disturbance that could put elevated activity in an unexpected window. it is worth being precise about what the K-index actually measures, because it gets thrown around constantly and rarely explained. Kp is not a measure of how bright the aurora is or how many particles arrive. It is a measure of magnetic disturbance, specifically how much the Earth's magnetic field wobbles at ground level, averaged across a network of observatories around the world over a 3-hour block. It runs from 0 to 9 on a quasi-logarithmic scale, so the step from Kp5 to Kp6 is a much bigger jump in actual disturbance than the step from 1 to 2. The reason that number tracks the aurora is the chain underneath it. A coronal mass ejection arrives carrying its own magnetic field. If that field is oriented southward, opposite to the Earth's field on the sunward side, the two can connect in a process called magnetic reconnection, and energy and particles pour into the magnetosphere. Those particles get funneled down the field lines toward the poles, slam into oxygen and nitrogen atoms in the upper atmosphere, and the atoms re-emit that energy as light. Green from oxygen at around 100 kilometers up, red from oxygen much higher, blues and purples from nitrogen. That entire chain hangs on the orientation of a magnetic field inside a plasma cloud, and that orientation is essentially unmeasurable until the cloud passes the spacecraft parked about 1.5 million kilometers upstream of us, which buys somewhere between 15 and 60 minutes of warning. Everything before that is modelling, which raises a possibility that somebody has already positioned himself for. Michael Zeiler is an eclipse mapmaker. Tomorrow will be his 13th total solar eclipse. He will be aboard a cruise ship in a Greenland fjord sailing as a guest lecturer, which is already a very good place to be, since Greenland gets totality with the sun higher in the sky than Spain does, and with a decent chance of clear Arctic air. And he is going to point a video camera north, not at the sun, north, away from the eclipse entirely to capture any aurora that might form during totality. A massive outburst from the sun, he says, would be the icing on his eclipse cake. What gets me excited, he told the Associated Press, is viewing rare phenomena. Think about what would have to happen for that shot to work. You need to be at high latitude, where the auroral oval sits. You need clear sky. You need 2 minutes of artificial night in the middle of the afternoon which the moon is supplying. And you need a coronal mass ejection to arrive late by roughly the right number of hours, so that geomagnetic activity is elevated during that 2-minute window rather than 9 hours earlier. Every one of those is plausible on its own. All 4 at once, in the same place, is not something that happens often. There are only scattered reports across the entire history of eclipse observation of anybody seeing aurora during totality, and the reason is arithmetic. Totality is rare. High latitude totality is rarer. Clear high latitude totality is rarer still, and a geomagnetic storm arriving inside a 2-minute window is a coin flip on top of all of that. The scientific value of such an image would be modest. Nobody would learn much about the corona or about the aurora that they did not already know. The rarity is the entire point. It would be a photograph of 2 completely unrelated systems, one orbital, one solar magnetic, happening to intersect in a single frame. And that is the 4th clock, and it is the only element of tomorrow that has not already been written down. Every other number in this video comes from an ephemeris or a table, calculated in advance, correct to the second. This one comes from a forecast issued 18 hours ago by a system that was wrong by 2 scale levels last week. So, 3 of the 4 clocks check out in modified form. One event became 2 consequences of one geometry. A rate forecast turned out to have 2 competing numbers. A planetary alignment turned out to be a permanent arrangement briefly visible. The 4th thing people believe about tomorrow does not exist at all. Part 13. 7 seconds that will never happen. The single most widely shared claim about tomorrow describes something that cannot physically occur. The claim is this. On the 12th of August 2026, the Earth will lose gravity for 7 seconds. And the reason we know about it, according to the claim, is a secret NASA document, a program called Project Anchor, which leaked in November of 2024 and revealed that the agency had known about this for years and had been quietly preparing for it, in some versions to the tune of billions of dollars. 7 seconds. A specific number, a named program, a leak date, all of the furniture of a real disclosure. None of it exists. That rumour has been circulating through the entire first 8 months of this year. It has appeared on TikTok, on Instagram, on X, on Facebook, on Threads, on Blue Sky, and across a long tail of conspiracy blogs. One of the earliest known viral references traces back to an Instagram account in late 2025. From there, it did what these things do. It got clipped, re-uploaded, narrated over stock footage, and reposted by accounts that had no idea where it came from. I want to take it apart properly, because it deserves better than a dismissal, and because the way it falls apart is genuinely instructive. The first leg is the paper trail, and this is the cleanest test available. Searches of Google, of Bing, and of DuckDuckGo turned up no reputable results about any project anchor leaking online during or after November 2024. Searches of Facebook and X found no posts where anybody discussed a project anchor at the time it supposedly leaked. Think about what that means. A genuine leak of a major NASA program leaves a wake. Journalists ask questions, researchers argue about it, someone posts the document, someone else says it looks fake. Congressional offices get emails. Even leaks that turn out to be nothing generate a visible trail of people reacting to them in real time. This one has no trail at all before the rumours describing it. The alleged leak of November 2024 appears to have been invented retroactively by the claim that references it. The document does not predate the story about the document. The second leg is the direct denial. A NASA spokesperson stated by email that the rumour is not true. The Earth will not lose gravity on the 12th of August. NASA has separately stated that a solar eclipse does not cause the Earth to lose gravity and has no unusual impact on the planet's overall gravitational force. Snopes rated the claim false. Fact Crescendo rated the claim false. Local astronomy officials have gone on regional news to say the same thing. And the third leg is the physics, which is the leg that actually matters, because if the physics were plausible, then the absence of a document would just mean the document was well hidden. Earth's gravity is a function of Earth's mass. That is the whole equation. The gravitational pull you feel right now is produced by roughly 6 times 10 to the 24th kilograms of rock and iron sitting underneath you. To reduce that pull, you would have to reduce that mass. There is no other mechanism, not alignment, not shadow, not orbital configuration, not the moon passing in front of the sun, and nothing that happens tomorrow moves any of Earth's mass anywhere. Now I want to be careful here, because there is a real phenomenon in the neighbourhood of this claim, and it is the thing that gives the hoax its foothold. The moon and the sun do exert gravitational forces on the Earth. Those forces are real, they are measurable, and you can watch them work twice a day at any coastline on the planet. Tides are gravity. That is not in dispute. But a tidal force is not a cancellation of gravity. It is a difference in gravity. The moon pulls slightly harder on the side of the Earth facing it than on the centre, and slightly harder on the centre than on the far side, and that difference across the body of the Earth is what stretches the oceans into 2 bulges. The effect is a fraction of Earth's own surface gravity, and it is already completely in the tide tables. Every port in the world has the numbers printed. There is no hidden component waiting to activate. As for the planets, the combined tidal influence of every planet in the solar system on the Earth is orders of magnitude smaller than the moon's alone. Jupiter is enormous, but it is also more than 500 million kilometres away at its closest, and gravitational influence falls off with the square of distance, while tidal influence falls off with the cube. The moon is small and close, which is why it wins. So the claim fails 3 separate tests: no document, an explicit denial, and a mechanism that contradicts the most thoroughly verified equation in classical physics. But here is the part I actually find worth thinking about, and it is not about gravity at all. It is about the date. Why the 12th of August? Why not some random Tuesday in March? Because the 12th of August already had something real on it. A genuine, precisely dated, government-published, once-in-a-century astronomical event, with official timetables and agency press releases and a NASA live broadcast scheduled. The hoax did not have to generate credibility. It borrowed it. It attached itself to a date that was already going to trend and rode the attention that the real event was generating. That is the trade, and it is worth naming clearly. A verifiable rarity, a total solar eclipse, the first over Iceland in 72 years, and the last for 170, got swapped out for an invented catastrophe. And the invented one travelled further, and this is not new. It is one of the oldest patterns in the relationship between the sky and the people underneath it. In 1910, when the Earth was due to pass through the tail of Halley's comet, spectroscopy had recently detected cyanogen, a toxic gas, in cometary tails. That was a real observation, published by real astronomers. What happened next was that the real observation got detached from the fact that a comet's tail is so close to a vacuum that passing through it has no measurable effect on anything, and a market appeared for comet pills and anti-comet umbrellas in sealed rooms. People genuinely believed they might not survive the night. Go back further and eclipses themselves were the trigger. An unexplained darkness in the middle of the day is about as alarming a thing as a sky can do, and cultures across the world built responses to it. Noise-making, ritual, the interpretation of an eclipse as a warning aimed at a specific ruler. Those responses were not stupid. They were the correct behaviour for a species that could see the event and had no way to anticipate it. What dissolved that fear was not scepticism. It was prediction. Once you can say in advance that the sun will go dark at a particular hour on a particular day, and then it does, the event stops being an omen and becomes a schedule. That is the single largest thing astronomy has ever done for the ordinary experience of being alive. Which is what makes the Project Anchor story so strange. We're in the era where prediction has won so completely that we hand out tables, accurate to the second, and the response is to invent an unpredictable catastrophe and attach it to the one date where the prediction is most public. The same thing happened to a comet. Part 14, The Comet That Isn't There. Among the events on tomorrow's viral convergence list is a comet with a tail stretching the distance from the Earth to the Moon. There is no such object in the sky. Let me go through what is actually up there, because the real situation is more interesting than the invented one, which is becoming a bit of a theme. The brightest comet currently visible is 220 per Mcnaught. It is a Jupiter family comet, and it has been doing something genuinely unusual. It went into outburst on the 30th and 31st of May this year, and then, having settled down, it went into outburst again on the 5th of August. 2 brightening events in 10 weeks, from an object that was not supposed to do either. As of early August, it had brightened to around magnitude 6 to 7. Its coma had grown to about 7.5 arc minutes across, and it was showing a tail of roughly 21 arc minutes. From 40 degrees north, observers describe it as easy in binoculars. Magnitude 6 is, technically, the traditional limit of naked eye visibility. Under a perfect sky, with dark adapted eyes, knowing exactly where to look. In practice, for almost everybody, this is a binocular object. It is a small fuzzy patch with a slightly brighter centre and a faint smear of tail. It is worth finding. It is not a spectacle. The other comet in the neighbourhood is 10P Tempel 2, which has already passed its peak brightness and is fading. It is too faint for the naked eye and needs large binoculars or a small telescope, and it is best placed for the southern hemisphere in early August anyway. The broad assessment from the observing guides is blunt. 2026 is not a great naked eye comet year. Now, about that tail claim, it is wrong, and it is wrong in a direction that is almost funny once you look at the numbers. The distance from the Earth to the Moon is about 384,000 kilometres. That sounds enormous, because in human terms it is. It is the furthest any person has ever travelled from home. But as cometary tails go, it is nothing. A genuinely great comet's ion tail can stretch tens of millions of kilometres. Comet Hyakutake in 1996 had a tail measured at well over 500 million kilometres, more than 3 times the distance from the Earth to the Sun. So the claim is unsupported, and it also badly undersells what a real great comet looks like. If somebody tells you a comet has a tail as long as the Earth-Moon distance, they are describing a modest comet, not a spectacular one. What is true, and this is the number that should have been in the posts, is that 220p Mcnaught's coma at its May peak reached roughly 235,000 kilometres across. That is about 1.5 times the diameter of Jupiter, around a nucleus that is probably 1 to 2 kilometres wide. Sit with that ratio for a moment. An object the size of a small mountain, temporarily wrapped in a cloud of gas and dust, wider than the largest planet in the solar system. And an outburst is not the same thing as a comet simply getting closer to the Sun and brightening on schedule. A scheduled brightening is smooth and predictable. You can plot it years in advance from the orbit alone. An outburst is a discontinuity. The brightness jumps by a factor of hundreds or thousands over hours or days, for reasons that are still argued about. A pocket of trapped volatile ice suddenly reaching the temperature where it converts straight to gas, a section of crust giving way and exposing fresh material, or the nucleus itself cracking. Whatever the cause, the comet stops behaving like an object on a known trajectory and starts behaving like something that is failing. That happened this year, twice, to the same comet, and we covered exactly how and why in the video from 2 days ago, so I will not rerun the argument here. The relevant point tonight is simply that the real comet story of 2026 is stranger than the fake one, and it got a fraction of the attention. That is now 3 times in one day. A total eclipse described as partial, a meteor rate quoted without its conditions, a comet invented with a tail measurement that a real comet would find insulting. Every one of them keeps the drama and discards the accuracy, and every one of them is downstream of something real that was, in each case, more remarkable than the version that replaced it. Which leaves one more piece of the framing to check. Everybody is calling tomorrow once in a lifetime, so why does Spain get another one next August? Part 15. 3 eclipses in 3 years. Spain is about to get 3 central solar eclipses in under 18 months. The 12th of August, 2026, tomorrow, a total eclipse, roughly a minute of totality, at sunset across the north of the country. The 2nd of August, 2027, a total eclipse across the southern tip of the peninsula, with up to 6 minutes and 23 seconds of totality, the path continuing into Morocco, Algeria, Libya, Egypt, Saudi Arabia, Yemen and Somalia. That is nearly 3 times more observing time than tomorrow, and it is one of the longest totalities of the century, and the 26th of January 2028, an annular eclipse, the Ring of Fire. An annular eclipse is worth explaining properly, because it is not a lesser version of a total eclipse, it is a different geometric outcome. As we discussed earlier, the Moon's orbit is elliptical, so its apparent size in our sky varies. When the Moon is near the closer end of its orbit during an eclipse, it more than covers the Sun, and you get totality. When it is near the farther end, it is slightly too small, and even at perfect alignment a bright ring of the Sun's surface remains visible all the way around the lunar disk. And because that ring is still photosphere, still the blinding surface of the Sun, an annular eclipse never gets dark. The corona never appears. It is never safe to look without a filter, at any moment. It is a spectacular thing to photograph and a completely different experience from totality. So, 3 central eclipses over one country in 18 months. Is that a pattern? No, it is clustering, and the reason is worth a minute. Eclipse tracks do repeat on the Saros cycle we talked about, 18 years, 11 days and a third of a day. But successive eclipses within one Saros series land about 120 degrees of longitude apart because of that extra third of a day. So a Saros series does not park itself over one country, it walks around the world. What is actually happening with Spain is that several different Saros series, each running its own independent schedule, happen to be delivering eclipses to roughly the same longitude in the same short window. There is no mechanism connecting them. It is 3 separate clocks striking near enough the same hour. Carol Mundell, ESA's Director of Science, called it exactly what it is, a lucky coincidence. Practically, though, that coincidence changes the calculus for anybody able to travel, and I think it is worth being honest about it rather than leaning on the once-in-a-lifetime framing. If you can only make one trip, 2027 is the better eclipse. 6 minutes and 23 seconds against tomorrow's 1, a higher sun, a drier climate along much of the track, which means substantially better odds of clear sky. Tomorrow is the opening of a sequence, not a final chance, and weather is not a footnote in that calculation. It is usually the whole calculation. The 1999 eclipse, the last one to cross mainland Europe, is remembered in Britain less as an astronomical event than as a mass lesson in August cloud. Enormous crowds gathered along the Cornish coast, and a great many of them experienced totality as the sky going dark behind an unbroken grey lid. The eclipse happened exactly on time. Most people did not see it. That is the risk profile tomorrow evening on the Atlantic coast of Spain, and it is why serious eclipse planning is really climate planning. You do not pick the place with the longest totality. You pick the place with the best combination of duration and historical cloud statistics, and then you keep enough flexibility to move on the day. The chasers going to Greenland and to inland Spain have made that trade deliberately, giving up a few seconds of duration for a meaningfully better chance of actually seeing it, unless you live in Iceland. Because for Iceland, none of that applies. Tomorrow is not the opening of anything. Tomorrow is it, the first this century and the last until 2196. The next Icelandic totality is 170 years away, and no amount of travel budget changes that if you want to see it from home, which is the point that the phrase once in a lifetime always obscures. It is not a property of the eclipse, it is a property of your coordinates. The same shadow, on the same afternoon, is a routine astronomical event to somebody who chases them professionally, a once-in-a-century national occasion in Spain, and a genuinely unrepeatable moment in Iceland. The sky does not distinguish. Where you are standing does, which leaves exactly one question about tomorrow that nobody can answer, and it is not an astronomical one. Part 16, the most predictable thing and the least. The position of the moon tomorrow is the most precisely known quantity in this entire story. We can state the second at which the axis of its shadow passes closest to the centre of the Earth. We can hand you a table of when the partial phase begins in Winnipeg and when totality ends in Valencia, and those numbers will be correct. We have been able to do this at increasing precision since Babylonian astronomers noticed a pattern in their records without having the faintest idea what caused it. Tomorrow's eclipse was calculable centuries before anybody watching this was born, and the eclipse of the year 2196 is already in the tables, and now list what we do not know. We do not know whether the sky over Galicia and Asturias will be clear at 8:30 tomorrow evening. We do not know whether the Perseids will deliver 43 an hour or 100. We do not know whether a coronal mass ejection that left the sun days ago will arrive 9 hours early, 9 hours late, or not measurably at all. We do not know whether the boundary layer over Iceland will collapse. We do not know whether anyone will photograph an aurora during totality. Every single one of those is downstream of a shadow whose arrival we can time to the second. Start with the scale we live at. A band of shadow 293 kilometres wide, crossing a planet 12,742 kilometres across, moving at 5,000 kilometres an hour, and the entire human problem reduces to whether you happen to be standing inside that band during the 90 seconds it is over you. That is it. That is the whole difficulty. Not the physics. The physics is finished, has been for centuries. The logistics. Widen it out. The moon is moving away from us at 3.8 centimetres a year, slower than a fingernail grows. But run it forward and somewhere between 600 million and a bit over 1 billion years from now, the moon will be too far away to cover the sun completely, and total solar eclipses will stop happening on this planet permanently. Which means that every human being who has ever seen totality, and everyone who ever will, is alive inside a window. A wide window in geological terms, a vanishingly narrow one against the 4.5 billion years the Earth has already been here. Widen it again. Tomorrow, a jet will fly at 460 miles an hour to buy 42 extra seconds. 80 balloons will go up over Iceland across 26 hours to measure 2 minutes of dark. A pair of satellites that can manufacture a 5-hour eclipse on demand will be in the wrong part of their orbit to watch the real one. Every one of those is an attempt to solve the same problem. The event is short, the shadow is narrow, and being in the right place is harder than understanding what is happening. And widen it as far as it goes. From anywhere else in the solar system, this does not happen. No other planet has a moon that appears the same size in its sky as its star. Mars's moons are far too small. The giant planet's moons are too close or too distant, or the sun is too shrunken. The 400-to-1 coincidence of size and distance that lets the moon cover the sun exactly, no more, no less, leaving the atmosphere exposed and nothing else, appears to be ours alone, for now. We have always assumed the sky is the unpredictable thing and the ground is where we are in control. Tomorrow inverts that completely. The sky is the one part of the day that is already written down. Everything human around it, the travel, the cloud, the forecasts, the expectations, the stories, is not. And there is a version of that inversion that goes further, and I think it is the real reason people cross oceans for 90 seconds. For almost the entire history of our species, the sky was the only thing that could be relied on. The harvest failed, the weather turned, empires collapsed, but the stars came back around on schedule, and the moon went through its phases and the sun rose. Predictability was what the sky was for, It is where we got calendars, navigation, agriculture, and the entire concept of a year. We inverted that within a few centuries. Now the sky is the settled part, and the ground is the uncertain one. We can tell you where the moon's shadow falls in the year 2196, and we cannot tell you whether a cloud bank will sit off the coast of Asturias in 22 hours' time. We can compute the debris left by a comet in the year 1079, and we cannot tell you how many streaks anyone will actually count. What is left, once the prediction is finished, is the experience, and that turns out not to be reducible. You can know every number in this video to every decimal place, and it does not tell you what it is like when the last bead of sunlight goes out, and the corona is suddenly there, and the horizon is burning all the way around you. That gap between the completely known and the entirely unprepared for is what everybody travelling tomorrow is actually chasing. So let me put the corrections in one place, plainly, because if you take nothing else from this, take these. The eclipse tomorrow is total, not partial. If you're in North America, you will see very little. 9% from New York, 4% from Washington, 3% from Detroit, and you will need a proper filter to see even that. The Perseids have 2 forecasts, not 1, and the darkest sky in 19 years can still sit above a below-average shower. The 6 planets are 2 easy ones, 2 difficult ones, and 2 you will not see. There is no comet with a tail from here to the moon, and nobody, anywhere, is losing gravity for 7 seconds. And the title of this video is honest, but not in the way the posts mean it. Nobody is ready, not because something dangerous is arriving, but because being ready would mean standing in 6 different places at once, awake at 4 different hours, under clear sky, with the right filter over your eyes, for events that last between 2 minutes and 1 night. Amir Caspi, who has spent a career building instruments for these 2-minute windows and is putting 4 cameras in the nose of an aircraft tomorrow to buy back 42 seconds, said the thing that I think should be the last word on whether any of this is worth the trouble. It's true the eclipse is short, he said, but it's still incredibly valuable, which leaves one thread genuinely open tonight, and it is the only part of tomorrow that nobody has already calculated. Somewhere between the sun and here, a coronal mass ejection is in transit. Noah thinks it arrives in the early hours, universal time, 9 hours or more before the moon's shadow reaches Iceland. 4 days ago, the same forecast system missed a storm by 2 full-scale levels inside an hour, and on a ship in a Greenland fjord, a man who has done this 12 times before will have a camera pointed north, away from the eclipse entirely, during the 2 minutes when the sun is switched off. If that cloud of plasma runs late by exactly the right amount, he gets an image of the aurora burning over the Arctic in the middle of the afternoon, under a black sun. If it runs on time, nobody will ever remember the forecast existed. We find out tomorrow.